Okay, from this set of practice problems that Bob Johnson put together, which I called mt2-2025a-prac.pdf. Okay, let's do question 3. I have a QR code over here going directly to that file. It's also in the description of the video. So this is actually an RC circuit problem, which is what makes it interesting. I think the RC circuit problems are things we want to practice. But this particular problem starts out with just a regular resistor and battery problem before it moves on to being an RC circuit problem. Let's do part A first. So the first part of this question says if the switch is closed, so closed looks like that. If the switch is closed, then what is the current I through the resistor? So let's draw a little current arrow like this, and then we could write down the loop rule. So we can say battery EMF minus IR1 minus IR2 equals 0. We went up, out the positive terminal of the battery, to the right through R1, same direction as our labeled current, so it's minus IR. Then we continued, that same direction is now down through R2, so our loop is going the same direction as our labeled current, so it's minus IR2, and then we're back where we started. We're at the negative terminal of the battery. So that gives us I is the battery voltage divided by the series combination of these two resistors, which is 10 volts divided by 300 ohms, which must be 0.0333 amps. 10 divided by 3 would be 3.33, yeah, 0.0333. Okay. Okay, now we extend the circuit. It's going to extend even more to the right in a moment, but we extend the circuit to the right by adding this capacitor C1. There's another switch S2, and then we're told that just before time 0, that both switches are open, and capacitor C1 has charge Q1 equals 0. So this capacitor that we just added has 0 charge before time 0. And these switches are open before time 0. And then what happens at time 0 is that these two switches, S1 and S2, are closed. And then there's some more stuff off to the right that we can ignore for now. So let's close switch S1. And let's close switch S2. And let's make it obvious that they're closed. All right. And then we want to know what is the current flowing through each of the two resistors. All right, so I labeled those two currents I1 and I2. So let's work out what I1 and I2 are at that instant. So this is actually kind of interesting. These RC circuit problems, they can actually vary quite a bit, and they're kind of interesting. So the thing is, at t equals 0, we close S1 and S2. Remember, closing a switch means that it allows current to flow. Opening a switch means current is not allowed to flow. And before that, before t equals 0, we have Q equals 0. Okay, so this capacitor starts out discharged. I'm going to call that Q1 because there's going to be a Q2 later. Now, so you know that the charge on the capacitor in these RC circuit problems immediately after you throw the switch is the same as the charge on the capacitor in these RC circuit problems immediately before you threw the switch. So the charge is still 0 on this capacitor immediately after you throw the switch. And so then if the charge is 0, then the voltage across this capacitor is 0. So I guess I could label these points here. Let me call this like point A, and I'll call this point B. So at t equals 0 plus, right? That's like an instant after we close the switch. We have VAB equals 0 because Q1 equals 0. So that means, VAB is Q1 over C1, and that's 0. So that means this looks like a wire at that instant, immediately after we close the switch. It doesn't look like a wire for long, but at that very instant it looks like a wire. So then, so no current flows through R2 at that instant, because why is that? Why does that make sense? So you know that I2, R2 is the same thing as VAB. VAB is like VA minus VB. I2, R2 equals VAB, and VAB is the same thing as Q1 over C1, and it equals 0 at t equals 0 plus, the instant after we closed the switch. So therefore, I2 equals 0 the instant after we close the switch. That's kind of interesting. It's a little bit, takes you a moment to grapple with that, I think. So it seems like all of this current I1 at that first instant is actually like charging the capacitor. I'm tempted to call this I3. Here, I can call this I3. So you can see that like at that very instant I2 is 0, so I3 just equals I1. Okay, meanwhile, what is I1? At that same instant, so you see we could say the battery voltage minus I1 R1, and now, well, okay, actually then we can say minus I2 R2 equals 0, but this was 0. So that gives us that I1 just equals the battery voltage divided by R1. Okay, so I mean, one way to see that is to say, oh, well, you see, if at that instant this is like a wire, then, a wire has no resistance, so it's like 10 volts battery voltage minus I1 R1, and you're just going like effectively through a wire at that instant. I mean, you don't want to think of a capacitor as a wire in general, but like when the capacitor has 0 charge on it, there's no voltage across it, so that's kind of like a wire. A wire is an equipotential. So I guess we could work out numbers for that. The battery voltage is 10 volts, R1 is 100 ohms, so this must be 0.100 amp. All right, so that was so that was question B. Question B was like just the instant after we close S1 and S2, we had I2 is 0, and we had I1 was 1/10 of an amp. So let's see what's next. Okay, so next is like for this very same circuit as drawn, switch is still closed, same configuration. After a very long time has elapsed, what is the charge Q on C1? Okay, so after a long time, that means like T is much bigger than whatever the relevant time constant is. We're going to work that out later. You say, what is Q1, the charge on capacitor 1? Well, after a long time, so you know that after a long time, you have dq dt approaches 0, because this charge approaches its asymptotic value. I mean, actually, if you looked at the charge on a capacitor charging up, it looks like it starts out at 0, and then it like at its maximum slope here, and then the slope gets smaller and smaller and smaller. And then eventually it reaches this asymptotic value. And by the way, like the current, which is the rate of change of this slope, so you have like, here's I. So we have I is dq by dt. See, that starts out at its maximum value, and then it gets smaller and smaller and smaller and smaller. So this is like the maximum value times e to the minus t over time constant. And this is like the maximum value, I don't want to say q0, I'll say q max, times 1 minus e to the minus t over time constant. I usually actually find the current versus time a little easier to relate to than the charge versus time. But this curve should be kind of imprinted on your brain also, both of these curves. Okay, so at some point this charge reaches its asymptotic value, so the current, which is charging it up, reaches 0. So that tells you that I3, which equals dq1 dt, that goes to 0. So, and then at that point, all of the current flowing from the battery, that's I1, must flow down through R2. So at that point, yeah, so at that point, I2 equals I1 and I3 equals 0. So now we can figure out, we want to figure out the voltage across the capacitor. That's what we're going to have to figure out to get the charge on the capacitor. So we can use the loop rule to write the battery EMF minus I1 R1 minus I2 R2 equals 0, because we really want this thing I2 R2. But this is actually the same current. So this is the same statement as the battery EMF minus this current I1 times R1 plus R2. So in fact, I1 at this very long time after we close these switches equals the battery EMF divided by R1 plus R2. And then, see, actually this is the voltage divider equation that I mentioned in a previous video, or it's going to be soon, it's not yet. So then VAB is I1 R2, sorry. I mean, it's really I2 R2, but I2 equals R1. It's really I2 R2, but I2 equals I1, because all the current flowing through R1 continues through R2 once I3 becomes 0. So this is the battery EMF times R2 over R1 plus R2. And what is that? Oh, gee, I drew this picture where you couldn't see it. I hate when I do that. Okay. All right. So this seems to be, okay, that's like, see, this is 200 over 200 plus 100. This is 2/3. So this is 2/3 of the battery EMF. That's actually kind of an annoying number. That's 6.667 volts. So then how do we know the charge on the capacitor? Well, VAB also equals the voltage across the capacitor. So this is charge on that capacitor divided by that capacitance. So, you know, like the fundamental equation for a capacitor is Q equals CV. So then that gives you that the voltage across the capacitor is the charge stored by the capacitor divided by the capacitance. So then if you want this charge stored on each plate of the capacitor, it's plus on one plate, minus on the other plate, then it seems like we have Q1 just equals C1 times 2/3 of the battery voltage. So that seems like 80 microfarads. Yeah. I guess we'll just multiply that out. Okay. So we have 80 microfarads times 10 volts times 2/3. We could ask Python, and that's 533 microcoulombs. So that equals 533 microcoulombs. Oh, that can't be right because it's different from the answer I got before. Okay, ha ha ha. So this is actually, like, I see it's kind of useful when I make mistakes sometimes if I catch them and correct them. So I wrote down a wrong number from the problem. It's kind of nice when exam problems have the relevant numbers written onto the schematic diagrams. So we're going to have another capacitor later called C2, which is going to be 80 microfarads. Turns out this capacitor C1 was 40 microfarads, so I'd written down the wrong number. You know, another like defensive strategy is if you like kind of label your own schematic, then if you like misread something, then at least everybody knows what you were working with. So 40 microfarads times 6.667 volts is going to be 267. 267, yeah. Okay. 267 microcoulombs. Sorry about that. Although I think like it's kind of useful when you see me make mistakes because then you know not to make that same mistake. So it seems like by the time this capacitor reaches its asymptotic charge, which means that I3 becomes 0, which means that all of this I1 just continues through R2, the voltage between points A and B, VA minus VB, also known as VAB, that is just a charge in this capacitor, Q1 divided by its capacitance, Q1 over C1. Okay, so Q1 over C1 is like this voltage AB. This voltage AB is 2/3 of the battery voltage. So then we take that 2/3 of the battery voltage times C1, and that gives us 267 microcoulombs stored on the capacitor. That means it's actually like, it's plus Q up here, it's minus Q down here. That's what happens after a very long time. You know, a couple people asked me recently in class, isn't it true that after a very long time, the voltage on the capacitor, isn't it true that after a very long time, the voltage on the capacitor equals the battery voltage? No, not necessarily. Not if there's like some kind of, you know, voltage divider effect like this. So in this problem, and in the problem I recorded an hour ago, there's like kind of a voltage divider effect like this. So the maximum voltage on the capacitor is actually smaller than the battery voltage because of this voltage divider effect. Whereas the previous problem, I think the first RC circuit example we worked out, I think didn't have that feature. Okay, so now I think we're going to say, like, this is like, you know what's going to happen. We're going to throw another switch, and something interesting is going to happen. So let me erase and set up the next part. But we know that the starting point for the next part of the problem is going to be that capacitor 1 has 267 microcoulombs on it. And let's see what happens. Okay, so after S1 and S2 had been closed a long time, but S3 stayed open, we found that the charge on capacitor 1 was 267 microcoulombs. And then before we did anything with S3, that stayed open, then we opened S1 and S2. So they had been closed before, now they're open. So now this charge on capacitor 1 has no place to go. It just stays there. And now, with these two switches open as they're drawn here, now we're going to close. Now, reset watch. And at t equals 0, we close S3. Okay, so we close S3. That's going to look like this. And now there's no resistor in between C1 and C2. So actually what happens here is going to happen instantly. That's kind of different from these. So I guess this is going to be plus Q2. And here's minus Q2. Yeah. Minus Q2. So in this problem, like actually what's going to happen after S3 is closed actually happens like immediately. It doesn't take any time to happen because there's no resistor here. It would actually be a more interesting problem if we stuck a resistor here somewhere between C1 and C2, because then there would be some RC time constant to move charge from C1 to C2, but that's not this particular problem. So now the question is, I think, what are the final charges on C1 and C2? Okay, so then, like, after, once equilibrium is reached, then what are Q1 and Q2? Okay. So now these two capacitors are in parallel, so they have the same voltage. So that means, right, so in parallel, same voltage, so that means Q1 over C1 equals Q2 over C2, but the charge didn't just come out of nowhere. The charge must be the same charge that was originally on Q1. So we know we have two equations now, basically. One is this thing, Q1 over Q2 is C1 over C2. The other is that Q1 plus Q2 equals this original value. It's like the previous value of Q1. So I'm going to call that, I'll just write it as a number because I didn't give it a different name. I should have given it some different name, like Q1 initial. So we have Q1 plus Q2 add up to this value because, like, what's going to happen is some of this charge will move over to here, like that. And then I guess, you're also going to have something like that. So you're going to move some of this positive charge over to here, and then also then you're going to make this a little bit less negative. This becomes less positive, this becomes less negative, this goes from 0 to being a little bit positive, this goes from 0 to being a little bit negative, and that stops when these two things reach the same potential difference. Well, actually it happens instantly because there's a wire there, so like instantly now these have to have the same potential difference. So what does this tell us? This tells us that Q1 over Q2 equals C1 over C2. Although I think actually C2 is bigger, so it's more convenient to write it upside down from that. So we'll say Q2 over Q1 equals C2 over C1. Let's make sure I did that right. Q2 over Q1 is C2 over C1. So that gives me Q2. So C2 is twice as big as C1. So Q2 must be 2Q1. Right? C2 over C1 is 2. So Q2 is 2Q1. Okay. So then what does that mean? That means that Q1 is going to be 1/3 of 267 microcoulombs, and Q2 is going to be 2/3 of 267 microcoulombs. So these two things add up to 267 microcoulombs, and it's a 2-to-1 ratio, and 2 is bigger, and they have the same voltage, so the bigger capacitance gets more charge. That makes sense. So then this is going to be, all right, so divide by 3, and that's 88.9 microcoulombs, and then twice that is going to be 178 microcoulombs. These numbers don't sound familiar. So, oh yeah, there we go. 88.9 and 178 is what I got when I worked this out yesterday also. Yeah. This could be an even more interesting problem if instead of S3 you had a resistor. And then I think you would have a time constant RC. G. Then is that the two capacitors in series or in parallel? And you would be moving charge from one to the other, and I guess it would stop when, like if you put a resistor here, I guess everything would stop when these two reach the same voltage. So you'd have the same end point, but then the question is, what is the RC time constant? Are C1 and C2 in series, or are they in parallel? Yeah, okay, so I think that's a pretty hard problem. I don't think we'd ever do anything that difficult on an exam. So I just tried to work this out, and I said, well, there's really only one variable here. It's Q2, because we had this constant charge. I call it Q initial is 267 microcoulombs we started with on C1, and then like kind of charge is like charging up Q2. So what's left on Q1 is just the initial charge minus Q2. So then that's a constant. So then I said, okay, here's the voltage on capacitor 1, and here's the voltage on capacitor 2, and that voltage difference divided by R, I drew a resistor in place of the switch there. That's going to be the current going from left to right here through this resistor I just added to the problem to give it a time constant. So that's like the rate at which Q1 is decreasing, and it's the rate at which Q2 is increasing. And so then I can just substitute, see now instead of Q1 I have Q0 minus Q2, and here's Q2. And then this is just copied from here. So then I can split apart this term because I want to get out the constant. So here's Q0 over RC1, that's just some constant. And then here's like C minus, in parentheses, I've got like Q2 over RC1 with a minus sign from there, and I've got Q2 over RC2 with a minus sign from there, but the minus sign's outside the parentheses. So then there's like the rate of change of Q2. So here's this constant term, I just copied it over there, and I can take this thing in parentheses and I can rewrite it as Q2 over R times some equivalent capacitance. And if you look at this expression, you know, this is like Q2 over R, and then you see this is 1 over C1 plus 1 over C2. And you know 1 over C1 plus 1 over C2 is 1 over C equivalent if they're in parallel. So you see I just replaced that. Oh. That's if they're in series. I'm sorry. That's if they're in series. Oh gosh. You know, okay, I don't like to hide my mistakes from you unless I mislead you. That's in series. So always remember, never forget, the way you combine capacitors in series is the same as the way you combine resistors in parallel. And the way you combine capacitors in parallel is the way you combine resistors in series. Okay, so you see I used the formula that I kind of am used to using for resistors in parallel, but this is of course capacitors in series. Okay, there we go. So these actually are in series, which kind of makes more sense. Yeah, obviously it makes more sense because the current through them is the same. I hope you don't mind my thinking aloud a little bit. This is like I just tacked on this digression because I said, gee, this happens instantly. Wouldn't it be interesting if it didn't happen instantly? What would that happen? What would that be about if it didn't happen instantly? Let's stick a resistor here instead of just having a piece of wire for a closed switch. What would happen? And I think I did this right. So this current going from here to here is just, see, that's like discharging Q1, it's charging Q2. And then how big is that current? It's this voltage difference divided by this resistance. So here's this voltage, there's the resistance. I think that's okay. I did all this so I could figure out what does the time constant look like. Like how do you combine the two capacitors to make this time constant? It wasn't obvious to me right away. So I wrote it out this way. And you can see that this is the same thing as Q2 over RC equivalent, but what kind of equivalent is that? This is the series capacitors. Because capacitors in series combine the way resistors combine in parallel. Maybe let's write that out while we're here and talking about mistakes. So resistors, let's do series and parallel. Okay, so resistors in series we have R1 plus R2, and resistors in parallel we have 1 over R1 plus 1 over R2, the reciprocal of that. You can also write that as R1 times R2 over R1 plus R2. Capacitors in parallel is C1 plus C2. In series, it's 1 over C1 plus 1 over C2, the reciprocal of that, which you can also write as C1, C2 divided by C1 plus C2. Okay, so remember that the way you combine capacitors in series is the way you combine resistors in parallel. And the way you combine capacitors in parallel is the way you combine resistors in series. So this expression that I wrote down for the equivalent capacitance is the series combination of C1 and C2. And I think that makes sense because the same current flows through these two capacitors. So I think that's how it makes sense that they're combined in series. So that was kind of cool. So actually, if you did have a resistor there instead of S3, then your time constant would be that resistance times the series combination of these two capacitors. So that would actually be, I think, 80 divided by 3. Yeah, I think it would be 80 divided by 3 is 26.7 microfarads instead of 40 or 80 microfarads. So if you put those two capacitors in series, then you get 26.7 microfarads. Here, let me just check that. 1 over 40 plus 1 over 80. And then there's 1 over 26.67. Yeah. Okay, well that was kind of fun. We made that problem a little longer just for fun. I think these RC circuit problems are tricky. That's why I'm like starting the videos with the RC circuit problems. I think we might have one more to do after we do. Okay. I'm going to end this video. The next video is another RC circuit problem.